Fantastic. All right, so we got... Okay, so we do have Scott, but we don't have Joe, and we don't have Eric. Okay, no problem. All right. Man, it's been a big week for you guys. You know, we got a lot done this week because you had a test that was a take-home test, and you had class on Tuesday, and you had class on Thursdays, and now you're having class on Friday. Man, we're just covering so much material. We were just learning like crazy. How did the assignment go for today?
It was easy.
It was easy?
Yeah.
Ah. Does everyone feel it was easy? Did anybody feel it was really difficult? Yeah. Now, here's the deal. All of that stuff that you did last time was formally how a derivative is done. I mean, that was what we were learning, is the thinking about how a derivative is a function and how we can use those ideas of limits to do derivatives. And we are going to no longer do that. We are now going to learn, as chapter 3.3 is called, what is differentiation rules. Differentiation, remember, is the verb, like for finding a derivative. So we're going to learn some rules about how to do this, that we don't have to go and reinvent the wheel all the time and keep doing them in the form of these limits. Now, one of those rules we learned the last time, we were talking about these things, where we said that the derivative, like if you have some function that is some constant times x to some power, okay? This is called the power rule. And if you have some constant time, that might be a 1. Heck, that might be a 1. Whatever, but the derivative of that is, you pull the b down in front, so it's a times b, x to the b minus 1 power. This is called, in your book, the power rule for derivatives, and it's by far the simplest kind of derivative to do. And you had a whole bunch of examples of that on that homework set for 3.2. Where, like, you had defined if the function was, 3x to the 4th power, and you worked and worked and worked and did the limit, and as the h approached 0, and you did the magic factoring, and you did the canceling, and so on. Whereas now we know by the power rule for derivatives, this is just 12x cubed. Because we just pulled the 4 down in front, and it took it, 3 times 4, and we lowered the power by 1. And in fact, we can keep playing that game and take second derivatives and third derivatives and so on. So we could have the second derivative, 3 times 12 is 36, and lower the power by 1, and it's 36x squared. Or in this case, we could take a third derivative, and we'd have 72x. Hey, what if we wanted to even have another derivative up here? Hey, let's start with a fresh equation here.
There would just be 72.
Yes, exactly. Let's say our function had been 72x. What is its derivative?
72.
72. I mean, because it's really 72 times 1 times x to the 0th power, but that's not very enlightening, is it? Times 1 doesn't do anything, and x to the 0th power is 1. So it's just, 72. Hey, what would the second derivative here be? So what is the derivative of 72? Another way of saying 72 is 72 times x to the 0th power. So let's see, 72 times 0 times x to the minus 1 is 0. Anytime you're taking the derivative of just a number, it's going to be 0. Because you've got that x to the 0 implied in there.
So if you graph that, what would it look like?
Well, a graph of some constant like 72 is just something like this, right? X, at any value of x, the value of f of x was 72, so its slope is 0. Good question. Your book actually has a name for that. It was derivatives of constants law or something like that, but basically anytime you do the derivative of just a constant number, it's just 0. Okay. So you don't have to play the game anymore of doing all of that business of limits and so on. The law works, by the way, just fine even if the exponents are negative. So for example, if your function f of x was 1 over x squared, one way to write 1 over x squared is x to the negative 2 power. So its derivative is negative 2x to the negative 3. There is one example where this doesn't work, but we're not going to get there. There's a problem if it's x equals -1. I'm sorry, if the power is -1. But we're going to deliberately avoid that at this time. Okay? You can get into a little bit of a problem with that. But as long as you just keep realizing, hey, we just got to lower this by 1. -2 minus 1 is -3. Pull that -2 out in front, and you've got it. This can get even more complicated if we add another rule to it, which I think your book calls something like the addition rule or something like that, where what they're saying is if you have some function, the way the book actually wrote it was something like, if you had some function h of x, and it's the sum of two other functions, it's perfectly okay to say that the derivative of h is just the derivative of f plus the derivative of g. Which might not seem that illuminating. But this is not only really useful, but actually like it makes common sense once you see it. So like if we had some function, let's just say f of x equals 3x squared plus x. It's two functions added together. One is 3x squared and the other one is x. Just take the derivative of each of them separately. So the derivative of f is 6x plus 1. You can just do each of the pieces separately. Well, that doesn't mean anything, right? By the way, it works for minuses too. So like if you had a g of x equals x to the 4th plus 3x, oh, sorry, minus, let's use a negative sign here, then g prime of x is 4x cubed minus 3. You can just hook them together that way. So those addition and subtraction rules of differentiation are just no big deal either. Now, last time we met, you might remember Matt was speaking in tongues. Do you remember there was high d low minus low d high divided by low d low or something like that? And you might have thought something's gone wrong with Matt. We always knew something would go wrong with him. Now we get to find out that Matt was right. We just have to figure out what he's talking about here. Another type of rule that we can apply these to is the product rule. Again, your book writes out in a way that is formally correct, but is not necessarily all that enlightening. Where they say that if you have some function that is written as like two terms multiplied by each other, the derivative of that function is just the derivative of the first times the second plus the first times the derivative of the second. Matt, what's your little sing-song thinking about that?
It's, let's see, that one, that's 1d2 plus
1d2 plus
2d1.
2d1. So he's saying like this is the first one and this is the second one. So he's saying 1 times the derivative of the second plus second times the derivative of the first. That's another way to think about it. But let me just show you as an example. Let's say you had some function that had a product in it. Maybe 3x plus 2 times 4x squared. It has a product. You can find the derivative of this function. Oh, could you do this using everything you did in the last unit where you found the limit? Yeah. Would it be fun? No. It would be a hot mess. Right? But all we got to do instead, let's use Matt's little 1d2 plus 2d1. Okay, so we're going to call this thing the 1 and this thing the 2. So the first one times the derivative of the second plus the second one times the derivative of the first one. And that's literally all there is. Now, your book is not going to let you leave it like that. But now you have to use your big algebra brains and start, factoring this and multiplying and simplifying. But it's done. Anytime you have an equation that can be written as like two terms that are multiplied by each other, the product rule will be helpful. I've never seen it written quite like this, but it makes perfectly good sense. This, I guess I was just writing down what he was saying, but whatever. But either one of these is fine. Notice that his rule is a little bit different than mine. I had the first derivative of the first times the second plus the first times the derivative of the second, but all I did is, this is his rule just written the other way around. Okay? It works. Fun rules! Fun rules. Man, you can well imagine that your book is capable of writing hundreds of questions about these things.
Yes.
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 No.
One more rule. The other one that Matt was speaking in tongues about, low d high minus high d low kind of thing. And that is a quotient rule. What if the function that you're working with can be written as, like, it's some number in the numerator, some function in the numerator times some function in the denominator. And I would say it's derivative of the first times the second minus the first times the derivative of the second all over the derivative of the, the second one squared. And let me double check because I often get that one backward. Yep, that's right. Matt called this term high and this term low because they're high on the fraction or low on the fraction. And Matt, what was your, I'm sorry, this is not equals, this means the derivative rather. Matt had another way of saying it. What was your thing? You said low d high minus high d low over low squared.
Yep.
Knock yourself out if that helps. If yodeling something about high d low minus low d high helps you, I am okay with that. So, for example, let's try one. What if your function was, I don't know, x squared plus 2x over 4x plus 1? How would we find the derivative of this? Could it be done using those limit laws like was apparently boring and easy last time? I don't know. Yeah, yes it could. But if we wanted to find its derivative, we could use these rules. Alright, it's low d high, let's see here, low times the derivative of the top, 2x plus 2, minus the top, high, times the derivative of the bottom, all over the bottom part squared. The book is not going to let you just leave it in that form. You're going to have to do all the factoring and distribution and association and some of that to cancel things out all over the place, but you'll get it after that. That is just algebra. Now, notice the mistake I have made a couple times before. Remember, it isn't like, alright, if I wrote out f of x equals this, I can't then write equals the derivative. This is not an equals here. Okay? This is the new thing. This is the derivative of the function. Whatever the function looks like when we did it, this other one, the derivative, explains what the slope is at all these different points. There's a ton of cool things you can do with this. One cool thing you can do is you can find the places where the slope is 0. The places where the slope is 0, take the derivative and then set them equal to 0 and find the values of x that make it equal to 0. That's a useful thing because that helps you find these places like here and here where it's a maximum or a minimum. I think your book actually does throw like one problem like that at you in this section, but that's something that's going to come more in the future in the book. Okay? Where they're going to be more often saying, hey, find, because that's actually often something we do in calculus, is we're finding what are the values of x where this is a maximum. F of x is a maximum. Well, they're going to also be the places where the tangent line has a slope of 0. Okay? You don't, I think you can make do that on one problem in this one. There's a mess, a real mess of these rules. We've only looked at a couple of them here. That power rule, which is so easy. Which is so easy that we've been just flinging around here like we knew what we were doing. I mean, I looked at this equation and I said, let's see, Matt's expression, low d high. So derivative of the high part here, 2x plus 2. Look at that, I just did it right here because I just pulled the 2 out in front, lowered that by 1. 2x plus 2. How did I know this was 2? Because derivative of 2x is going to be 2 times 1 times x to the 0 power equals 2, right? This just takes a little bit of exercise. Now, you would think that your book, which loves having so many problems at the end of each section, would go bonkers at this point, where they would just be like, I'm coming up with 100 problems for you. For whatever reason, the book decided today to start showing a little restraint. And there really aren't that many problems at the end of this section. In fact, it's surprisingly few. It is on page 200, and I think it's 63. Page 263. Numbers 107 through 112 odd. I'm sorry, 121 odd. And 137 through 141 or 143. 141 odd. And number 149. Now here's the deal. That's not that many problems. And actually, over here, I think it's numbers 119 and 121. It asks you to graph them. You don't have to do that. Or it says like, plot them on a graphing calculator and show it to your teacher or something like that. I don't care. Okay, that doesn't strike me as, yeah, it would be very educational to plot them. But I don't really want to go around and look at your graphing calculator and be like, oh, you did it, how nice. Okay, Scott's going to do it on Desmos or whatever. No, however it all works, we'll be fine. We'll get there. All right, so that's the assignment for here. You'll notice it's just not that many. I mean, there's like 10 problems here, 3 problems here, and 1 right there. It's not that much. All right? All right, let's go ahead and get started on that so that Scott still has a chance to head off to wherever he needs to be at 1:30. All right?